All right, dude, we are live. What's up, guys? This is Dem Keys, and today we are going to be learning. Finally, we are going to get into training neural networks. So, in the last stream, we learned about using PyTorch's AutoGrad system to. Wait, give me a second. My stream manager is not showing the stream, so let me just refresh the page and make sure that the stream is going. Okay, we're good. So, in the last stream, we learned how to use PyTorch's AutoGrad system to calculate the gradients of the loss for our neural network. So it would calculate the gradients of the loss with respect to the parameters of each layer in the neural network. And now we are going to be, so the next step to do after you've calculated the gradients is to use those gradients to update your weights and biases. And that's what we're going to be doing today. And that tends to be an iterative step where, okay, so how it's supposed to work is you pass input to the neural network. You initialize the neural network with random weights and biases. You pass input to the neural network. You get the output, calculate the loss, calculate the gradients, and then based on the gradients, you update your weights and biases by a small amount. And then you restart this process. You repeat the whole process again, now with these updated weights. Again, you pass in the input and you get the output, calculate the loss, calculate the gradients, update the weights. You keep repeating this step until your loss is, let's say, a minimal amount. I need to look into that bit as well, because there is a thing where, so as far as I understand, you don't want the loss to be, like, you want the loss to be a minimal amount, but you don't want the loss to be near zero. Let's say, I guess, because there is such a thing as underfitting and overfitting, and I need to learn about that. Well, we are going to learn about that once we learn how to train the neural network. But I do know that, yeah, having a, let's say, a perfect loss score isn't necessarily always a good thing. For the time being, though, we're going to be learning how to optimize the weights and biases of our network through an iterative process, which is basically training. So after yesterday's stream, uh I took some time to mess around with this code that was, well, it wasn't necessarily this code. It was, I think, more like, uh this. I think this was the code. We would initialize a random input, random weights, random bias, and also a random expected output. Then we calculate our actual output, and then we use binary cross entropy with logits to calculate the loss, given our predicted output and our expected output. And then given that loss, we would call loss.backward, which would then update the gradients, or it would calculate the gradients for the loss with respect to the weights and biases. Uh, I had to I had to take some time to actually understand the structure of what was going on here, because I understood the fact that it was updating the weights and biases, or it was updating W and B. But I kind of got confused looking at the shapes here because I had forgotten. Like, I was trying to visualize it. Let me just put it that way, and I was having a hard time visualizing it, which is why I had to take some time to think about it. Because I kept connecting it to this. Um, I kept connecting it to nn.linear, where you specify an in feature or an in feature, a number for in feature. You specify the in features and the out features, and I remember that I'd created this sort of picture in my head about what exactly nn.linear was doing. I was trying to visualize it as a neural network layer, as a hidden layer, and I'd forgotten what that visualization was. So I was just trying to remember that again, and then connect that to these shapes. I don't know if I'm explaining it very well, but yeah, it took me a little bit to get that. But basically, with nn.linear, what I understood, and this was a while back, I'd understood this and I'd made the visualization in my head. What nn.linear is doing when you specify in features and out features, the out features are the neurons in the layer, and the in features are the number of features that are going to go into each neuron. Meaning each neuron is going to have a weight matrix containing a value for each of the in features. So I was just trying to remember that, and I was also trying to like do the matrix calculation and like remember exactly how this is meant to be. How, what am I trying to say? I was just trying to remember what I'd figured out. I don't know, a couple of weeks back, and I was just trying to remember that, I guess, or well, that's just remembering. Either way, okay. We are gonna look into optimization. This is a different page. This is a more complex topic, which we are going to look into later on, because this is for more complex models. Apparently, this is a thing where you partially train the model, or you train like sections of the model, from what I understand. I don't know if you're training like sections, or if partially training means training all of the or optimizing all of the weights at once. Like when I think about partially training a model. Oh wait, no, this is not saying partially training. Where did I read the partial training part? It says here partial loading. Uh, okay, so anyways, when I read this, I still haven't fully understood this thing, but when I read this, my guess was that, or what I was imagining was a situation where we are training sections of the network as opposed to the entire network at once. That's just what I'd imagined. I don't know what's actually happening here. We're gonna look into this much later on, not now. Because I feel like the network that we are currently working with doesn't really require that. And also the example given here is a convolutional neural network, not a feed forward network. So actually it's a mixture. It's a mixture of convolution and feed forward. But yeah, either way, what was I saying? Yeah, I don't think I need to look into this right now. I'll look into it at some point, but I do want to familiarize myself with convolutional neural networks and recurrent neural networks before I go into this. In fact, a bunch of the other tutorials and stuff, they do go into convolutional neural networks and recurrent neural networks. A bunch of the other architectures that get explained, they use CNNs and RNNs quite a bit. They don't just stick with feed forward neural networks. So I would like to get at least a basic understanding of CNNs and RNNs. I kind of already understand the concept with RNNs. Um, yeah, I kind of already understand the concept with RNNs, and I have an idea of how CNNs work, but it's a very, very, very basic idea. Like I have a visualization of how the calculation is being done, but that's about it. In terms of the weights that are required and whether there are biases and um, how things like max pooling, for example, get used, I have no idea. So I need to look into that at some point. Actually, not at some point. I need to look into that once when I'm looking into convolutional neural networks. Okay. So we're gonna start reading this. Um, okay. Now that we have a model and data, it's time to train. No, it's time to train, validate, and test our model by optimizing its parameters on our data. Training a model is an iterative process. In each iteration, the model makes a guess about the output, calculates the error. So this is what I was explaining earlier. Ca- Sorry, give me a second. Let me drink some water. Okay. Uh, in each iteration, the model makes a guess about the output, calculates the error in its guess, which is the loss, collects the derivatives of the error with respect to its parameters. Um, so that's okay. That's calculating the gradient and optimizes these parameters using gradient descent. For a more detailed walkthrough of this process, check out this video on backpropagation from 3 Blue 1 Brown. Speaking of 3 Blue 1 Brown, I recently found out about a library that this person had worked on. Um, it was called Manim, I think. Yeah, I think it's called Manim. It's a Python library. Actually, I think the initial library was no. I think even the initial thing wasn't. I don't know. You can read up on the history of it, but yeah, this person does and even used to do it. Like they've been doing it for a while. They do math tutorial videos, and I don't know what else, like what other tutorials they do, but they definitely have like a lot of math related tutorial videos. And there's a lot of their videos would have animations in them. So this person had made a tool to help them create those animations, and at some point I think they released it to the public, and then the community made a community edition of that library, and now that is being maintained. And there's also the original version, which 3B1B is using themselves. But yeah, it was interesting to find out that there is this math animation library, because it's gonna be useful. It's a Python library, and you can use it to make a bunch of different types of animations, which I've been, okay. So there have been situations where I was trying to set up an animation, and my best, how do I say this? The best idea I could come up with was to animate it using Unity and Timeline, or well, Unity's Timeline tool. I have done that in the past, and it works. It works to a certain extent. It has its own pros and cons. But I do also want to try out Manim at some point. I would be doing, of course, I would be doing all of the calculations myself for the movement and stuff like that. That's one of the things with coding the animation. You have to do quite a bit of the calculations yourself. I'm expecting this tool to have, I'm expecting this library to have certain features that do aid us in the animation, aside from the actual, like, drawing and stuff. All of that stuff is definitely available, but I'm talking about like very specific movements, like, um let's say, for just as an example, I'm not saying that the library actually does help you with this, but let's say, for example, you had an object and you wanted the object to follow a certain path that you specify using like a spline curve or something like that, using a set of points, and you wanted the position animation to be interpolated between all of these points. So I'm expecting the library to have some sort of facility for that kind of thing. I'm not saying that the library does have for like that specific scenario that I'm talking about, but like, when you have these kinds of scenarios, I'm expecting the library to have some kind of functions that help you with those kinds of things. That being said, I'm gonna have to explore the library and find out exactly what it's capable of doing, because from what I've seen, there's quite a bit that you can do with it, at least from the examples that they've shown. But yeah, yeah, I'll I'll uh, I'll probably explore it someday, because for the time being, I'm getting deep into scikit-learn and PyTorch. Um, I'm doing both linear regression and neural networks. I'm studying both of them side by side, because the linear regression stuff and other stats related stuff, I'm going to be using it in Kaggle, and just in general, I'm interested in it. I'm glad that Kaggle is teaching the data science related stuff, because just learning linear regression, just learning the API itself, I should say, I wouldn't have learned about the concept of underfitting and overfitting. Just as one example of stuff that I wouldn't have learned. I would only be introduced to this if I was looking into some kind of tutorial for linear regression. And Kaggle does introduce it, though Kaggle is not introducing it for, I mean, in that specific course that I'm looking into, Kaggle is not they're not, what was I about to say, explore, expose, looking into. Kaggle is not introducing it in the context of linear regression. They are introducing it in the context of decision tree regression, which is also something that I need to explore. I haven't had the chance to explore decision tree regression yet, but now I have a much better understanding of what's going on than I did, let's say, a couple months back. Because a couple months back also, I had I'm gonna have to go back, and I'm gonna have to go back to my VODs channel and check when that was, but it was a couple months ago. I'd started going through the Kaggle course that teaches you, basic, like, machine learning stuff, and the very first basic thing that it taught us was decision tree regression for making a prediction. And at the time, I didn't fully understand what exactly was happening when you would fit the model and when you would make a prediction and stuff like that. But they kind of introduced those concepts to us, fitting the model, making a prediction based on whatever has been fitted into the model, and or rather based on whatever the model has been trained with, I should say, making a prediction and then evaluating the model as well, All of those things, they were introduced in that Kaggle course. And at the time, I barely understood what I was doing, but I just kept on digging more and more. And I had to take like to be honest, I had to take like a different path to understand what was going on, because the path that I took, uh, that path helped me understand the idea behind fit and predict. So at least, okay, with linear regression, we're going to get back to this neural network stuff in a bit. Hold on. At least with linear regression, when you call the fit method, you're basically asking the model to calculate the line of best fit. So when you call the fit method, it gives you a bunch of slopes and a bunch of y-intercepts, or maybe it's one y-intercept. No, I think it's a bunch of y-intercepts and a bunch of slopes as well. I mean, it depends on the size of the data that you're fitting the model with. And then based on those coefficients and intercepts, which is what it's called in scikit-learn, based on those coefficients and intercepts, it's gonna make future predictions. It's gonna make predictions on future data that you give it, new data that you give it. I feel like understanding that part has helped me, because when I looked into, like, when I started exploring other things that scikit-learn allows you to do, like k-means clustering, for example, um, it helped me understand that, okay, when you call fit, this is happening. When you call predict, that is happening. But yeah, I have to explore decision tree regression, and I feel like now I have a much better understanding of, at least like I've built up a much better base understanding. That's going to help me understand decision trees and decision tree regression much better. I there's still quite a bit of exploration that I have to do in terms of decision trees and decision tree regression, but that exploration is going to be a little easier now than it was previously. Okay, let's get back to this. Oh yeah, I after reading Three Blue, One Brown, I had kind of like my thoughts kind of branched out. Um, yeah, I do want to look at Manim as well at some point later. Is it called Manim? I think it's called Manim. I think it's called Manim. Yeah, and yeah, there is there are two versions of it. One is the one that's used and maintained by Three Blue, One Brown, and one is the community edition, which is, well, used and maintained by the community. Okay, prerequisite code. We load the code from the previous sections. Okay, so this was where we loaded the training data from the fashion MNIST set, and then we loaded the test data. And then using data loaders, we load, no, hold on, no. We loaded the data set, the training data set, and the test data set, and then we loaded the data from each of those data sets using data loaders and batch in batches of 64. Okay, right. So then we define our neural network class. Okay, and then this is our, okay. Should I spend time writing this down, like rewriting the whole thing again? I kind of want to do that. It's a waste of time, but I kind of want to do it. Right. So let's create a new notebook so um, it's not trying to, analyze all of those code cells each time. What all do we need here? So we need torch as tch, then from torch dot nn, no, actually no, import torch dot nn as nn, import torch dot nn dot functional. I don't remember what that's supposed to be. Get, oh, wait. Give it a second. Also, I need to save this. This will be notebook 04, I believe. KNB04. Okay, we are just waiting. We need the IntelliSense. No suggestions. Okay, great. Is it torch data? I don't think it's torch data. Why is it doing that? Oh, all right. Let's try that again. Let's try running this. Maybe after it runs, it's gonna be fine. Or do I need to activate the environment? No, the environment is active. Okay, we are just waiting now. Okay, I didn't take this into account that we're gonna have to do a certain amount of time wastage, but I guess it is what it is. Let the thing run, let it take its time, and once it's done, then it'll be slightly faster. Okay, looks like it's recognizing it now, and hopefully soon this will be done executing. In the meantime, if I do run this, dude, I need a better system, dude. Like, holy shit, this is bad. So, okay, I need to import Fashion MNIST from Torch Vision, and I think from datasets, I need to import dataset and data loader. I think I also need to import NumPy. I think so. No, I don't think we're doing any NumPy stuff right now, but like I'll import it anyways. Okay, finally. Great. Functional as fn. Then from Torch Vision, import dataset. Oh, is it this? Oh, it's torchvision.datasets, I think. Import um, fashion MNIST, and where was data loader? Uh, was it here? No, it's not. It's not part of this. Was it part of, where was data loader? Let me take a look at the code. Oh, it's utilities. Okay. And here we are just supposed to import, here we import torch vision dot datasets as datasets. Okay, so we don't need this. From torch dot utilities dot, what was it, data? Yeah, import data loader. I guess that should be it, but let's throw in matplotlib and numpy. Numpy as np, import, let's throw pandas in as well. Why not? Import matplotlib.pyplot as plt. Okay. While that gets done, we can, oh shit, I missed the ad timer. So there's going to be an ad playing in, I don't know, 10 seconds or something. Right. So we first need to load the data set, right? So we do train data. Actually, we need to create the class. So we'll do my neural network or one. Then we do nn.module because the neural network has to inherit from nn.module. And then in here, we define init. What was it? Self. Self.flatten equals nn.flatten. Then what else was there? Linear relu stack equals, this is just, I'm just doing this from memory and like just thinking of the stuff that I'm gonna need in, wait, the ad played and finished as well, and I just completely forgot about that. All right, whatever. Yeah, the ad is over. Okay, great. So we need, this is our first linear layer. This takes in, this has 700 and something in features, and I think 512 out features. Then we have relu. Then we have this again, linear, 512, 512. Then we have relu, and then we have linear, but this time I think it outputs 10 features. Yeah, I think so. Okay, so then we have our forward method. In forward, oh, we're also supposed to take in x, right? So x equals self dot flatten x, and then what else? I think at that point we just say logits equals self dot linear relu stack x, and then we return logits. That's our forward thing, right? Did I miss something? Okay, the network is fine, and the forward method is fine as well. Okay, and then here we can define the model object here itself. Or actually no, we don't need to do that. We'll just run the class here, or create the class here. We'll run this code and create the class here. And then here we need to import the data sets. So datasets.fashion mnist. We The root is supposed to be torch data, I believe. Yeah. Um, train is true. Let's explicitly specify all of them. I'm not sure what transform is supposed to. Oh, transform as in transform into. Then what is target transform? Because if transform basically tells you how you want this data to be presented, what is target transform? Oh, is target transform how the data is going to be loaded by a data loader? Fuck's sake, dude. Let me scroll. Oh, fuck off. Hold on. Hold on. We can do this. We can do this. Okay. Finally. Transform. A function slash transform that takes in a pill image and returns a transformed version. Okay. Target transform. A function slash transform that takes in the target and transforms. That doesn't tell me anything. Hold on, dude. Let's open this up separately and see if there's a better explanation. Because we want. Oh, wait. I think I also need to import a thing for tensors. I think for two tensor. Where was it though? Was it in this? No, it wasn't in this. Where was it? The two tensor thing, I need to import it. Oh, it's from torchvision.transforms. Okay, from torchvision.transforms, import to tensor. Right. Okay. What else did I need here? Oh, download. Download is definitely false. And then transform is to tensor. Oh, now I get it. Okay, this is a callable function. So this is we are passing in a function to this. This transform does not support torch script. Okay, convert a PIL image or ND array. Wait, so this function doesn't take in any parameters. This function doesn't take in any parameters. So how are we passing in? Wait, I'm curious. Actually, it might mention it here, right? In transform. Oh, it does say it takes in a PIL image. Let's try passing in. Okay, let's create a function here. Let's say def, I don't know, call o1, whatever. And we'll print out the type of A. So let's see if I pass in call o1, what gets printed out. Missing one required positional argument. Okay. All right. Let's say called. All right. It gets. Okay, dude. It gets called. So I'm trying to understand how this is working, because we are passing in a callable. It says it's a function slash transform that takes a PIL image. How am I accessing the PIL image? Because, okay, it takes in a PIL image and returns a transformed version. Okay, let's return a numpy array. So let's say np.array 0, 1, 2. All right. If I do this and then I try to access the training data set's data, what gets printed out? Training data set is not defined. Oh, okay. It still has the data. It definitely still has the data. So hold up. If it has the data, where's this data that I just put in? Transform array so and so. Okay. What if I do to tensor? Then what? Transform to tensor. Okay. Right. I am not getting this. I'm not understanding what happens in to tensor exactly. Yeah, I think I need to look for to tensor to understand what happens there. Because there might be something very specific. This is something silly to focus on, but I'm just curious. Transforms to tensor. Okay. Convert a PIL image or ND array to tensor and scale the values accordingly. This transform does not support torch script. This says this is a class. This transformation should not, wait, because the input image is scaled to 0 to 1, this transformation should not be used when transforming target image masks. See the references for implementing the transforms for image masks. Okay, so toTensor, toTensor is a class. I was assuming it's a function. Okay, so we are passing in. How is this working? Okay, so let's try asking Perplexity. Let's try asking Llama. In PyTorch, how exactly does toTensor transform the fashion MNIST data? What exactly is going on there? And how would I go about implementing my own version of toTensor? Okay. In PyTorch, the two-tensor transform is a crucial component for preparing data, especially image data, for use in neural networks. Here's a detailed explanation of how two-tensor transforms the fashion MNIST data and how you can implement your own version of it. What two-tensor does: input format. The fashion MNIST dataset contains images in PIL image format or as NumPy arrays. These images have pixel intensity values in the range 0 to 255. Really? Oh, see, I was about to say that no, hold on. It's not 0 to 255. It's 0 to 1, but I think 2 tensor is what's doing that. Yeah, I think that's what 2 tensor is doing. Uh well, maybe not the only thing. It's probably doing other things as well, but that's definitely one of the things that it's doing. It's changing the range, or more simply uh normalizing the values. Okay, conversion. The 2 tensor transform converts these PIL images or NumPy arrays into PyTorch tensors. Specifically, it changes the data type and scales the pixel intensity values for PIL images or NumPy arrays with um, uint8, so unsigned integers, unsigned 8-bit integers, which is basically bytes. It converts the data to a float tensor and scales the pixel values from the range 0 to 255 to 0 to 1. The shape of the data is also transformed from so-and-so for NumPy arrays or PIL images to so-and-so for PyTorch tensors, where C is the number of color channels, H is the height, and W is the width. Example of transformation. Okay. Transforms are to tensor. Okay. All right. Right. Implementing your own version of 2 tensor. To implement your own version of 2 tensor of the 2 tensor transform, you can create a custom transform class that performs the necessary conversions. Custom 2 tensor, call, self, and image. All right. And then it returns the tensor. So, oh, maybe I should be looking into callable classes. Yes, I should be looking into callable classes. So let's try defining a class. Let's say my call o1 define call self a, and then we return. Actually, let's print the type of a, and I'm guessing because this is callable, so when we pass the class in, then it calls the class as if it were a method, and then it passes the data in. So that's probably why we are not seeing any data being passed in here. We just need to specify this. I guess it makes it easier for the programmer to just specify 2 tensor, and then internally this constructor is gonna call 2 tensor and pass in the data. Let's try that. Let's see what happens if I pass in my call. That did not work. Was my assumption wrong? Did I miss something here? Hold on. Okay. Call method that takes a PIL image as, okay, let's try, hold on. Let's try a equals my call o1, and then we call this and pass in I don't know, sum01 string. Right, so that works. When we do it like that, it works. What if we just return A? Is that gonna work? No, that still doesn't work. Okay, I'm wondering if Llama is getting it wrong, or if I'm doing something wrong, because it could be either. Uh, the name of the variable, the name of the argument shouldn't matter. Just what the thing is doing, and it seems like the call thing is working perfectly fine. Like the calling mechanism is working perfectly fine. Okay. Uh, Hold up. When exactly does the transformation happen? I need to look into that as well. Let's try accessing data. Okay, let's try this. Oh, there it is. There it is. Okay. Oh, okay. So it is being called. It is being called. Let's just test something out. Okay. Let's say that. Yeah. Okay. It is being called. But it's only called when you actually try to access data, not when you initialize the data set. I was assuming that it's done during the initialization, but turns out it only does that during when you call. Though, is it each time you call that it does this? Okay, I guess so. So my guess then is that each time it grabs a small piece of the data that you're trying to access, and then it passes that to tensor, which then converts it to a tensor after doing some processing, and then returns that tensor. All right, great, cool. Now that that has been now that that is clear, we can move on. So then we have test dataset. And from what I understand, just setting train to false makes it a test data set. Let me just look at the code and confirm. Oh, let's be polite. Llama was right. Um, it didn't get it wrong. Thank you. Okay. Okay, dude. I was just saying thanks, but right, cool. You do you. Where was I? Fashion MNIST, optimizing datasets. What was I doing? Yeah, okay. So we have the test. Oh, let's take a look at this. Hold on. Train optional. If true, creates a data set from train images. Otherwise, creates it from images, which is the test images. Oh, okay. So they have like separate sets for training and testing, and that's all part of the 60,000 images, or actually no. I think the test data set was, it says 10K here. Does that mean it's 10,000? Um, oh, if I just type this, it should give the information. Yeah, it's 10,000. Okay. Number of data points, 10,000. Okay. What else? What else? Oh, you know what? I still need to look into. Oh, let me ask Perplexity. In Fashion MNIST, what's the difference between what? Transform and target transform. All right. In the oh, let's not scroll. Okay. In the context of PyTorch's Torch Vision datasets, such as Fashion MNIST, the transform and target transform parameters serve distinct purposes. The transform parameter is used to modify or augment the input data, which in the case of Fashion MNIST are the images. This can include operations like converting PIL images to tensors, normalizing pixel values, applying augmentation techniques, and more. Okay. Target transform. The target transform parameter is used to modify or transform the target labels instead of, no, the target labels associated with the input data. For classification problems like Fashion MNIST, where the labels are integers. Oh, okay. All right. So target transform is for the labels, and transform is for the data that um, the labels are associated with. How am I trying to say? Because okay, so each of the images has a label associated with it, which basically classifies it under that specific category. I don't remember how many labels there are, maybe 12. I don't know. So each image has a label. It turns out target transform has to do with the labels, and transform has to do with the data. For example, you might convert integer labels to one hot encoded tensors. Here's an example where lambda is used to convert integer labels to one hot encoded tensors. Um, what is one hot? One hot encoding, hold on, let this finish. One hot encoding is a technique used in data processing to convert um, wait. One hot encoding is a technique used in data processing to convert categorical data into a numerical format that can be understood and processed by machine learning algorithms. Here's a detailed explanation of how it works and its key aspects. One hot encoding is a method that transforms categorical variables. Wait, that was data pre-processing, not just processing. Okay. Uh, Categorical variables into a binary format where each unique category is represented by a separate column. This process ensures that the categorical data can be used in mathematical calculations and by machine learning algorithms, which typically require numerical input. So, one hot encoding is just, wait, hold on. It says where each unique category is represented by a separate column. For a second, I was about to be like, is one hot coding just associating each label with a number? But I think it's a little more complicated than that. Because it's saying that each unique category is represented by a separate column. That's not the same as associating it with like an individual number. This process ensures that the categorical data can be used in mathematical calculations and by machine learning algorithms, which typically require numerical input. Okay, I'll read up on this later on. Right. So now we move on to loading the data. So we have train data equals data loader dataset. We pass in the training dataset and uh, batch size. Did we have to give shuffle? No. Okay. Batch size 64. And then we do the same thing for test. All right, cool. So that is done. Now, hyperparameters. Hyperparameters are adjustable parameters that let you control the model optimization process. Different hyperparameter values can impact model training and convergence rates. Read more about hyperparameter tuning. Give me a second. I've noticed this thing. I tend to have moments where I'm able to read stuff easily versus, or well, and moments where I'm just not able to read that easily. I'm going to keep pausing in between because I have to go back and make sure that I read the thing correctly and even understood the thing correctly. And there are times where, like just now, where I can read the thing and understand it like quick and then move on. Okay. Hyperparameter tuning with ray tune. Hyperparameter tuning can make the difference between an average model and a highly accurate one. Often simple things like choosing a different learning rate or changing a network layer size can have a dynamic impact on your model performance. Fortunately, there are tools that help with finding the best combination of parameters. Raytune is an industry standard tool for distributed hyperparameter tuning. Okay, so a while back when I had looked into when we had first started learning about like this, and actually recently as well, I got this thought that all right, so I need to experiment with different neural network configurations to see how they impact the performance of the network and the prediction of the network in general, how they impact the performance, because the prediction also comes under performance and the speed, I guess, also comes under performance. So yeah, in general, how different configurations like different layer sizes and different weights and what else? What else? Different number of layers, not just layer sizes. How all of these different things can impact the network's performance. And I think I just learned what exactly that's called. It's called hyperparameter tuning. Though In this case, oh, so hyperparameters can be anything, right? I guess even the layer size would be a hyperparameter. I need to look into that. Actually, you know what? Wait. What exactly would classify as a hyperparameter? Okay, hold on. Am I able to zoom in, make the text a bit bigger? I think that's better. Right. In the context of machine learning, hyperparameters are parameters whose values are set before the training process begins and which control the learning process of a model. I mean, the network size is like by that logic, the network size would also be a hyperparameter, right? Here are some key points and examples that would no to clarify what constitutes a hyperparameter. Definition: hyperparameters are configuration choices that determine how a machine learning algorithm learns from the data. They are set by the user and are not learned during the training process. Examples of hyperparameters: you have learning rate, model architectures. Oh, okay, there you go. The number of hidden layers, the number of neurons in each layer, the type of activation functions used in neural networks, and so on. Optimization algorithm: the choice of optimization algorithm itself, such as gradient descent, stochastic gradient descent, atom, etc. Regular, re, there's that word again. Regularization, regularization parameters. Parameters like regularization strength in lasso or the dropout rate in neural networks, which control the model's complexity to prevent overfitting. Batch size, the number of samples used in one iteration of the training process. Number of epochs, the number of times the model sees the entire training dataset during training. Train test split, train test split ratio, the proportion of data used for training versus testing. Okay. Kernel or filter size, this is probably for convolutional. Yeah, in convolutional neural networks, the size of the kernels or filters used in convolutional layers. Pooling size, the size of the pooling layers in convolutional neural networks. Distinction from model parameters: hyperparameters are external to the model. Oh, wait, did they mention weights at all? They didn't mention weights and biases. The weights and biases are model parameters. Hyperparameters are set. Oh, weights and bias. Okay, so that's where the definition comes in. Hyperparameters are configuration choices that determine how a machine learning algorithm learns from data. They are set by the user and not learned during the training process. Weights and biases are updated during the training process, so they are not hyperparameters. Okay, dude, we learned something. Holy shit. We learned what hyperparameters are. Because I've seen this term mentioned in the past because I keep up with ML and AI stuff on Twitter, and I follow a bunch of people who like not just people who are posting about the latest flashy AI tech. I keep up with people who actually understand the tech and explore the tech side versus just exploring a flashy new product that users can use. And so because of that, I'm exposed to a lot of the technical talk because these people are explaining various things, right? And I've seen the word hyperparameter pop up many times. And I was like, what is the difference between a hyperparameter and just a parameter? Like, is it like some higher dimensional stuff that like I'm not even able to imagine at the moment? It sounds silly to say, but like when I say higher dimensional stuff, I meant higher dimensional in the programming sense, like how we have multi-dimensional arrays. I mean in that sense. I was like, is it something like that? Why is it called a hyper parameter? But yeah, okay. Impact on model performance, distinction from model parameters. Hyperparameters are external to the model and are not set, no, and are set manually before training begins. In contrast, model parameters are internal to the model and are learned from the data during training. Okay. Impact on model performance. The selection of hyperparameters directly affects the performance and behavior of the model. True. Yeah. Yep. Incorrectly set hyperparameters can lead to underfitting or overfitting, while optional hyperparameters no, while optimal hyperparameters can improve the model's generalization ability. Tuning hyperparameters. The process of finding the best hyperparameters is known as hyperparameter tuning or hyperparameter optimization. Um, this can be done using methods such as grid search, random search, or cross validation. All right, cool. Great. So, ray tune. Right. So, fortunately, there's a tool that no, there are tools that help with finding the best. Okay, I'm back to having trouble with reading again. Fortunately, there are tools that help with finding the best combinations of parameters. Raytune is an industry standard tool for distributed hyperparameter tuning. Raytune includes the latest hyperparameter search algorithms, integrates with TensorBoard and other analysis libraries, and natively supports distributed training through Ray's distributed machine learning engine. Oh, so are we also going to be using Raytune here? Okay, we define the following hyperparameters for training: number of epochs, the number of times to iterate over the dataset, batch size, the number of data samples propagated through the network before the parameters are updated. Wait, the number of batch samples propagated through the network before the parameters are updated. Okay. So here I'm trying to remember the thing where even though you define, like, you can define a certain number of in features and out features, but then you can still pass in multiple samples to that same layer at once, and it's going to return those same samples. Okay. Okay. Hold on. I need to try and remember this. So here's what we're going to do. We're going to create a new thing. Okay, A equals uh, tensor 123. No, actually not. Um, I'm trying to do multiple. Okay, here we do 123 and then 4, 5, 6. So then we're going to pass in two batches, right? Okay, so let's say LO1 equals nn.linear. This takes in 3 input features and gives out, let's say it gives out 3 output features. Okay, B equals LO1A. and then we print out B. Right. We have an issue. Oh, hold on. Wait a minute. Wait a minute. 3. Wait. Must have the same D type. Oh, is this the issue? That they're not decimals? All right. Okay. So we we defined or we described we mentioned 3 input features per sample, but then we can pass in any number of samples that we want. And the samples. Oh, yes. Okay. So this I dude, I have to keep reminding myself of this thing. So just let me do it. Um, where was it? Linear. So in linear, it is mentioned that when you call this, the input shape can have any number of dimensions before. I need to keep reminding myself that yes, this is the case. Okay, right. So I have refreshed my knowledge, and now we can continue. So what were we doing? So yeah, we okay. So when it says 64, does that mean that if we come back here, does that mean that it's basically passing in, so like how I have 2 samples here, we are passing in 64 samples with each sample containing 700 whatever colors, which is each sample is one image. Does that mean that it's passing in 64 samples at once, and then the network is like returning all of that data at once? Because like if it's able to return this data that I have here, it should be able to return the other data as well, right? Though, um, so if I do this, okay, so this means it's going to be returning a value per sample, meaning it's going to be returning 64 values. Okay, all right. Wait, I still need to find out if we are passing in the entire batch at once or like what's going on. Okay, for batch, for batch in enumerate. So that's the entire batch, isn't it? And then we have x, y. Okay. We pass in the entire x. Yeah, that's the whole batch, isn't it? We are basically passing in the entire batch. Is there also an explanation here? Nah, it's gonna take me some time to like okay, I'm gonna have to read a bunch of these things as well to get a better understanding. I just jumped to the end. I'm sure there's, you know, oh, yeah, yeah. There's quite a bit for me to. I need to read a bunch of these things. Okay, hold up. All right. Okay. So I found someone here. Okay, cool. So here's what we're going to do. I'm going to raid this person. Their name is something. Their name is West RL1. We're going to raid this person. Uh, okay, right. So I wish I could stream for longer, but unfortunately, I started my stream late. And so, the talking portion of the stream, it has to end here. I was supposed to do my sculpting practice yesterday, but I didn't do it. I want to say I'm going to do it today, but I don't know if I'm going to do it. Uh, Hopefully. Let's see. I don't know. But yeah, that being said, I hope you guys have a nice day, and I'll see you all next time. Peace.